My name is Seth Kinoshita, and this is Lab 2 of Physics 2211, Motion of a Falling Object. In this lab, we will explore Newton's second law and the momentum principle, discussing how it applies to the lab. Then, after initial conditions are established, we will discuss how data was collected using each of the three models. Then, we will look at the results and compare the models before ending with conclusions and what-ifs. The purpose of the experiment was to observe the motion of an object and generate three different position versus time graphs, an experimental model through tracker and two computational models, both with and without drag force. The goal was to model the effects of gravity and drag on the falling object's motion. A key concept in this lab is Newton's second law, usually written as F is equal to ma, but as seen in the previous lab, it can be rewritten in terms of momentum, seen in the equation below. In this experiment, we are assuming mass is constant and the initial velocity is zero, but unlike last lab, the net force is not assumed to be zero. Rather, an object dropped from rest will have two forces acting on it as it travels towards the ground. These two forces are the drag force and the weight force. The drag force is a frictional force, meaning it acts opposite to the direction of motion. The formula is seen below, with b being the proportionality constant, v being the object's velocity, and j hat being the unit vector in the y direction. Based on this formula, the drag force is directly proportional to the velocity squared, so as an object gets faster, the drag force should also get larger. The other force is the weight force, or the force of gravity. This formula is simply the mass of the object multiplied by the gravitational constant g, with j hat as the unit vector in the y direction again. In freefall, when these two forces become equal in opposite directions, this object has reached something called terminal velocity, meaning it will not get any faster than its current speed. Let's keep that in mind for later. The experimental procedure was first to record a video of a paper ball being dropped. Then it was to analyze the video using tracker and to extrapolate the data. The third step was to manipulate the starter code in GlowScript to create two computational models, one with just gravity and one with gravity and drag. The fourth step was to create a position versus time graph to compare all three models, and then draw conclusions. So, the initial conditions were determined to be 0 meters per second for the initial velocity because it started at rest, and the initial position was determined based off the axes placed in the tracker shown to the right. Motion is in the negative y direction, and the system was determined to be the paper ball, while the surroundings were the earth and the air. As you can see here, I pinned a graph of data that looked like this. We can ignore the top x position, we're only looking at the y position, and this is a preview of the results because it shows the experimental data that will be compared against the two computational models. The first computational model, seen here with the skeleton code, was gravity only. To write this, I modified the skeleton code to write a program for the motion of the ball that only accounted for gravity. Since there is no drag force, we can assume that this b proportionality constant is 0. The time of 0.0725 is an indicator of how long the ball was in the air during the video. Also, the drag force, Fd, was set equal to the 0 vector because it's being neglected for now. Finally, both the momentum principle and the position update formula were applied to the code to get an accurate measure of the motion of the ball. The second computational model was with gravity and drag. The initial conditions, along with the position and velocity update formulas, remain the same in this model, seen here. However, a proportionality constant, seen here, was included because the drag force was not 0. This was calculated using final velocities and trial and error to find a b that fit the dataset. Additionally, the force of drag is no longer the 0 vector, and the formula discussed earlier was just plugged in to this code. Data was collected from both computational models. A comparison graph was made between experimental data, the gravity-only model, and the gravity plus drag model. Overall, most of the data is similar towards the start, but the gravity-only model starts to drop off a little bit due to it not accounting for the drag force. However, the data between the gravity-drag model, seen in yellow, and the experimental data, seen in blue, matches well, indicating that the experimental data did have a force of drag. Some outliers in the experimental data, like this point right here, can likely be chalked up to having to manually track in the tracker software, and variable frame rates from the recording camera. So some what-ifs and what does it mean as we conclude this experiment. So which models predict terminal velocity, and what does terminal velocity mean for net force? So both experimental and the gravity models predict terminal velocity because the y position ends up increasing linearly instead of logarithmically, indicating a constant velocity that indicates a net force of 0. And the net force is equal to 0 at terminal velocity because, as defined earlier, terminal velocity happens when the force of gravity and the force of drag are equal in opposite direction. And assuming that there are no other forces acting on the object in freefall, the net force would in fact be 0. So what if the object were thrown downward with an initial velocity? So terminal velocity itself would be the same, but the time to reach terminal velocity might be different. To show this, I put initial velocity in the starter code with the drag force and compared the two. As you can see on the graph on the right, the object reaches the same positions and the lines have the same slope, but the one thrown with initial velocity downward actually had an initial velocity that exceeded its terminal velocity, meaning it has a greater force of drag and it reaches the same y position in a greater amount of time. To see this, just look at the y position of negative 1 meters. The object from rest reaches it at 0.4 seconds, but the object with an initial velocity reaches it at around 0.45 seconds. Thank you.